Okay, I hope the screen is visible and I'm audible too. So let's start today's session. The recording has also been started. Okay. Good evening, everyone. Myself, Arka Roy. I'm working as a Prime Minister's Research Fellow in the Department of Electrical Engineering, IIT Patna. And I will be your NPTEL PMRF TA for this course on discrete time signal processing. This course is offered by Professor Mrityunjay Chakravarti, who is a professor in the Department of Electronics and Communication Engineering, IIT Kharagpur. So let's move to today's content. So today we'll first solve the questions that has been there in week 4 quiz, and then we'll go for a quick recap of the content that has been covered in week 5. So in week 5, the main topic is basically the multi-rate signal processing, which comprises of uh, these operations like decimation, interpolation, polyphase decomposition, and additionally, as because we are discussing decimation and interpolation, with these two in a effect, the upsampling process and downsampling process comes into the picture. So we'll try to we'll try to go for a recap of those two things also. And then we'll solve some questions related to week 5 content, that is basically the multi-rate signal processing questions. And after that, we'll end with a short Q&A session. So let's solve the week 4 quiz. So in week 4 quiz, the topic was basically the discrete Fourier transform or DFT and the properties of DFT. Additionally, we'll solve some questions of Z transform also that has been there in week 4 quiz. So week 4 quiz mainly consists of DFT and its properties and the Z transform. So let's start solving week 4 questions. So this is the question number 1 of week 4, which states that we have given a xn input sequence xn, which has a Z transform of x of z, and the corresponding ROC is given as 1 upon 3 less than mod z less than 2. So therefore, the question is we need to find the Z transform of x of minus n. And associated with that, we need to find the ROC also, as because we know that in case of Z transform, the final outcome of Z transform actually corresponds to several sequences. It is only the ROC that basically makes the Z transform unique. So we need to find the ROC also for this particular question. So let's first start with solving what is the Z transform of x of minus n, and followed by that we'll check what is the ROC of x of minus n. Okay, so Z transform of x of minus n, as per the definition, I can write it as x of minus n e to the z to the power minus n. So I can write it as x of minus n, z to the power minus n, and n is running from minus infinity to infinity. Now, I can change the variable. Let us consider minus n is equals to m. Then at that condition, if n goes to infinite, m goes to minus infinite. And if n goes to minus infinite, m goes to plus infinite. So the limits of the summation will run from infinity to minus infinity. So in many of the cases from last 4 weeks, we have solved numerous amount of questions where we had changed the limits and the limit was just the opposite that was there initially. So we also have talked about, for example, if this is a signal and this is spreaded from minus infinite to infinite. So if I calculate the area under the curve, so if I integrate the signal from minus infinite to plus infinite or from plus infinite to minus infinite, it actually yield to the same area value, that is A. So the integration doesn't depend on the direction or on the this particular path, like from which direction to which direction we are integrating or summing the signal. So in case of analog signal, we do the integration. In case of digital signal, we do the summation operation. So I can write it as x of m and z to the power m. Okay. Now I can change the limit as m is equals to minus infinity to plus infinity. Then I can write it as it is that x of m, and then I can write it as 1 upon z to the power minus m. So if I factorize this, it will be z to the power minus m whole to the power minus m. So the minus will make the power positive and it will be z to the power effective. So now this is basically coming in the form of some z transform representation. So I can write it as x of 1 upon c. So z transform of x of minus n is basically x of 1 upon z. Now we have got the, someone is joining. Okay. So we have seen that the z transform of x of minus n is basically x of 1 upon z. Now we are left with the ROC, that is the region of convergence. So we need to find what is the ROC of the particular sequence. So for that, so in the question it was given that x of n. Is this an issue or something? Mm, okay. So when xn was given and the z transform was x of z, at that time ROC was 1 upon 3 less than mod z less than 3. Now in case of x of minus n, we can see that the z transform is now x of 1 by z. So I can modify the ROC just by changing the argument of z. So now it is 1 upon z less than 2 less than 1 upon 3. So I need to calculate the ROC in terms of mod z. So therefore, let me just reciprocate the inequality. So I will get 3 greater than mod z greater than half. So I can write it as just by interchanging the positions. So 3.5. So for this particular question, for x of minus n, the z transform is x of 1 upon z, which has a corresponding ROC of half less than z less than 3. So let's just check the solution for that. So the option D is matching. So therefore, option D is the correct answer for this particular question. Okay. Let's move to question number 2. So in question number 2, it is given that we have a signal y of n, which is related with an input signal x of n by this form. So x n minus 1 minus n. So the variable of the particular signal is small n and it is shifted with n minus 1 factor. And it is time reversed also. So that is why it is written that yn is a flipped version of xn, as because we are doing some time reversal. So additionally, the xn has a DFT of x of k. Now in the question, we need to find for y of n, what is the DFT. So we need to find what will be y of k. So let's solve y of k. So y of k by the DFT equation, we can write it as y of n e to the power minus j 2 pi k n divided by n. Let us consider the sequence as n number of samples. So the summation will run from n equals to 0 to n minus 1. So I can write yn as x of n minus 1 minus n, and then e to the power minus j 2 pi k n divided by capital N, and n is from 0 to n minus 1. So now we can see that we can change the variable. So let us consider n minus small n is equals to m. So when n goes to 0, m will be n minus 1. And when n goes to n minus 1, then m will be n minus 1 minus n plus 1. So therefore, it will be m is equals to 0. Fine. So it is just the same thing. Now the m is running from n minus 1 to 0. So again, we can do this. We can say the same argument that we can sum the signal from any direction and the summation will yield to the same result. Therefore, I can change the I can just interchange the limits of the summation. So that is what I will do directly. So let's just interchange the limits of the summation. So m is equals to 0, then n minus 1. So I can write it as x of m e to the power j 2 pi k by n, and then n I can write it as, so n I can write it as n minus 1 minus m. So I can just write it as n minus 1 minus n. Okay, fine. So therefore, I can even further break it down to individual components. So 0, n minus n, and then x of m. And then I can write it as e to the power minus j 2 pi k n into n. Second component, I can write it as e to the power minus j 2 pi k n into minus 1. And let me just erase this part. And I can write the last component as e to the power minus j 2 pi k n into minus 1. So I will start with this, solving this particular form. So let me just copy this part in the next page. So this is what the sequence looks like currently. Now we need to, I can see that n will cancel with each other, and e to the power minus j 2 pi k. This is equals to cos 2 pi k and minus j sine 2 pi k. So this is basically 0, and cos 2 pi is equals to 1. Any cos 2 pi, any multiple of 2 pi inside the argument inside cos, if it is multiple of 2 pi, then the output will be 1. Therefore, I can simplify it as x of m. Then this whole thing, it will basically converge to 1. Then I can write it as e power plus j 2 pi k n. And then I can write it as e power j 2 pi k m divided by n. and the summation is running from n is equals to 0 to n minus 1. So I can see that this particular exponent is not dependent on m. So therefore, I can take this out from the summation. So I can write it as e to the power j 2 pi k divided by n. And then summation m is equals to 0 to n minus 1 x of m e to the power j 2 pi k m. And sorry, so it is just m only. So m divided by n. So we can consider that e to the power j 2 pi k divided by n, and I can write it as n is equals to 0 to n minus 1 x star of m e to the power minus j 2 pi k m divided by n, and then I am taking a overall star. So if the star goes inside the conjugation operation, conjugate of any conjugate number, that will lead to the initial thing, that is xm only. And if I do the conjugation operation, so it will effectively lead to e to the power plus j2 pi k m by n. So we know that I can take this conjugation operation after the summation also. So I can write it as e to the power j 2 pi k divided by n. And then let's just move the summation operation inside the uh, bracket, and then I can write it as x star m e to the power minus j 2 pi k m divided by n. And then we can write a whole conjugate over here. So this part, so this is just for illustration. And then I can start over here again. So e to the power j 2 pi k divided by n. So this is what? This is the TFT of, so I can write it as TFT of x star. Okay, it will be small x, as because the uh, DFT is taken on the time domain signal, which is small x of m. And when we get the DFT, I can write it as x of x star of k. So therefore, I can write it as e2 pi k by n. And then there will be conjugate, and then there will be x of k. So in this way, I can get the final output over here. So I can see that which of the option is coming the with same representation, that is option A. So yk is equals to x star k. So this is k divided by n. So this is k. This is k e to the power 2 pi k by n. So option A is matching with the final solution. Okay, I guess no one's trying to join. Okay. So so the second question, the final answer is this one, option A. Okay. So let's move with the third question. So the third question is basically x of n. Let me change the color. So n is equals to 1 minus 1. Then there is another one. So this is 1, then 0, 0, 0. Okay. And k is running from 0, 1, 2, 3, 4, and 5. So that means this is a 6-point DFT coefficient index. So we have been given 6-point DFT coefficient index, as basically the DFT index k is varying from 0 to 5. So this is a 6-point DFT index. So we need to find uh, we need to evaluate yn, which is also a 6-point IDFT of x square, the DFT square of x of k. So therefore, yk we can write it as x square of k. So I can write it as the dot product between the two DFTs. So in the theory, so theoretically, let us consider yk, or let me change the name of the signal. So let us consider this gk, and gk is basically we can get the gk by taking dot product between two different uh, DFTs, that is HK and WK. So we have seen that in case of DTFT, in the DTFT domain, if there is a multiplication in the time domain, when it will do in the time domain, it will be converted to simple convolution or standard convolution. However, in case of DFT, in case of even in Z transform also, in the Z transform domain, if there is multiplication between two signals, then when we go to the time domain or inverse Z transform domain, so then we'll see that we'll get convolution between two signals. However, in the case of DFT, when we apply the dot product or multiplication, direct multiplication thing in the time domain or in the inverse DFT domain, it will basically be the circular convolution between the corresponding time domain sequence. So that means the circular convolution between Hn and Wn. So likewise, in this particular question, we can see that y of k is equals to xk dot product with xk. So that means if I take y of n inverse DFT, I will get circular convolution between xn and xn. That means we have to take circular convolution between the same signal. So let's start with solving the circular convolution. So for that matter, I need the sequence that I have written over here. So let me just copy the sequence in the next page. So this one is basically the sequence, and I need to actually create the circular convolution between the same signal. So I'll replicate this part again. So 1, 1, 0, 0, 0. And in the last class, I had shown you that how to calculate the uh, circular convolution. So we'll multiply each of the element with its subsequent signal. So in this element will be multiplied with all the elements that is present in the subsequent signal. So this will be 1, then -1, then 1, then 0, then 0. Okay. Then -1 will be multiplied with each of the elements that is there in the subsequent signal. So that will be -1, 1, -1, 0, 0, 0. Then again, this will be multiplied. So, and I'm shifting one place. When I'm multiplying with the next sample or with the next sequence value, so I'm shifting the multiplication position. So for this case, this will be just the replica of the original signal. So 1 minus 1, then 1, then 0, 0, 0. Fine. Now we'll be multiplying this 0. Then I guess let's join. So over here, we'll be multiplying with 0. So there are 6 values. So 0, 0, 0, 0, 0, 0. 1, 2, 3, 4, 5, 6. Okay. So then again, there will be 0, 0, 0, 0, 0. 1, 2, 3, 4, 5, 6. And then last one is again 0. So it will be 0, 0, 0, 0, 0. So now what I will do is that I will add all the values. So I will add all the values over here. So it will start with 1, then -2, then 3, then -2, then 1, then 0, 0, 0, 0, 0, 0. Okay. So in case of DFT, in case of circular convolution, if let us consider yn, or let me just change the name of the signal, otherwise it will make confusion. So let us consider we have two signals, hn and wn, and hn has a support of let's say n components in the signal or n sample values, and wn has support of n number of components in the signal. So if I do the circular con between hn and wn, so then the output will have max of n comma m. That means this much number of samples will be present after when we get the output of the circular convolution. So in this particular case, we can see that there are two sequences, and these sequences are apparently the same sequence, and both the sequences are having a total number of 6 points. So therefore, max of 6,6, max of 6,6. So it is 6 only. So output of this particular circular convolution will have only 6 sample values. So here I can see that it is exceeding 6 sample values. So what we need to do is that we have to consider from the first element, and we have to search for total number of 6 elements. So 1, 2, 3, 4, 5, 6. So this much is fine. So I can write it as go to, let me just change the color over there, and I can write it as 1, 2, 3, 4, 5, 6. So this is my first phase of 6 components, and here I can see some of the samples are also left, which is the output of standard convolution. So what I will do is that I will take this thing once again, and I will append this part under this particular first 6 sample sequence. So I can write it as 0, 0, 0, 0, 0. So I can see there is one sample shortage, so I will not write anything. So I will consider that there is no sample. And then what we'll do is that I will take an addition again, and I will get the final result of the circular convolution. 1, 2, minus 3, minus 2. Then sorry, this will be 1, and last element will be 0. So the final answer for this particular question is 1, minus 2, 3, minus 2, 1, 0. So let's just hop around the options and let's see which one is the correct answer for this particular question. So let me just write the final answer. So yn is equals to this, and let me copy this part also for reference. So I can paste it over here. So our yn is this one, and let's check which one is the correct answer. So it is 1, 2, minus 3, minus 2, 1, 0. So this option is C. Okay. So we have solved this question, which has which was basically dealing with the circular convolution. So in the DFT domain, if we have given the multiplication or dot product of two signals, when we take the inverse DFT, we'll get back the circular convolution between the two signals. That is basically given in the question. Okay. So the next question is, we have been given a 4-point sequence x of n, and the 4-point sequence is having this kind of representation that is given. And the k is running from 0 to 3, obviously, as because we have been given 4-point sequence, and so the DFT will also be 4-point DFT on here. So we need to evaluate y of n, which is a 4-point IDFT of this sequence. Okay. So I can write it as y of k is equals to basically e to the power minus j by k, then x of k, and then we need to find what is y of n, that is the IDFT. So in case of IDFT, I can write it as 1 upon n. So in this particular question, so n is basically total number of samples will be 4, So I can just replace it with 1/4, but let's stick with the original equation. So it will be phi of k e to the power j 2 pi k n divided by n. That is total number of samples present in the cell. And the summation will run from k is equals to 0 to n minus 1. So I can write it as 1/4, and then I can write it as xk. So mind it is capital Xk, as because in the time domain we represent the signals with small letters, and in the DFT domain we represent the signals with capital letters. So it will capital of Xk, and then e to the power minus j sorry minus j pi k followed by e to the power j 2 pi k n divided by n, and k is running from 0 to is 1/4, then x of k, and I can simplify it as e to the power j 2 pi by 4, and then I can take k out, and then I can write it as n minus 2. And again, k is running from 0 to 3, and that is what basically y in this. So this is basically the representation of y. And from the theory also, we know that when we multiply any exponent, complex exponent, with EFT, then what we will get, that is basically the circular circular shape by that particular exponent factor. So here I can see that exponent factor for this particular thing is basically 2. So you can even get the idea like e to the power j. So it would be in the form of e to the power j 2 pi k uh, um, and subsequently n divided by n. So here let me just replace this capital N by 4. So this is 4. So I can write it as e to the power minus j. So I can write 2 pi, then k and 4. This is I am taking to the standard representation. However, there is no value over here. So that means I need to adjust this 2 and 1/4 with some factor. So that factor will be 2. So that means e to the power this 2 will cancel this 4. So that means we are getting the same representation e to the power minus j pi k. So if I replace this particular thing with this representation, so I will get the final yn is equals to this much. And we know that whatever samples are there in original xn, that will be shifted by 2. So I can write that x of n is equals to, so the sequence is given as 1 0 0 minus 1. So 1 0 0 minus 1. So the output yn is basically the circular shift of x of n by factor of 2. So therefore, I can write that yn. So let us consider that. So what we need to find over here, that is the original, that is the sequence of y of n. So in this case, x of 0 is equals to 1, x of 1 is equals to 0, x of 2 is equals to 0, and x of 3 is equals to -1. So everything will be shifted by its components. So the y will have y0, y1, y2, and y3. That is what we need to find. So y2 will be x0. That is because this will be shifted by 2 amount. So y2 will be 1. Similarly, y3, it will be how much? It will be x of 1 as because this has been shifted by 2 amount. So this will be 1, 0. So we have got what is y2 and what is y3. Now let us consider for y0. I can do some calculation over here. So I can just copy this thing here. So let's copy this part. So this is what we have actually got from the last page. That is what I'm referring from the last page. This is the thing. So here from last one. So therefore now we need to calculate what is y0. That means we need to evaluate this particular sequence at n equals to 0. So I can write it as 1.4 and summation x of k, and k is running from 0 to 3. And I can write it as e to the power j 2 pi by 4 k, and there will be minus 2. So this will be effectively 1/4, then x of k, then I can write it as e to the power j minus I k. Okay, and k is running from 0 to 3. I'm just not writing that particular thing again and again. So it will be x of k, and e to the power minus j pi is basically cos of pi, and sine n pi is equals to 0. So I can omit that sine thing, and cos pi is equals to minus 1. So I can write it as minus 1 to the power k. So I can further simplify it as x0 minus 1 to the power 0, then x of 1, then it will be minus 1 multiplied, then x of 2, then it will be multiplied with 1, and then x of 3, and then it will be multiplied with minus 1. So here it is given that, um, so I can write it as 1/4. So the sequence that we have been given, that these two will cancel with each other. So it will be 1, and it is so here it will be 1 x of 0, and then it will be x minus x of 3. So this is how I will get y of 0, and then let me just take another page. So we had started with solving what will be x of n. So x of n is equals to 1, 0, 0, minus 1. And this was basically shifted. So we started with this particular position. Now I don't know what is there in case of 0th position and what is there in case of first position. However, at n equals to 2, I will get the shifted version. So this will come over here. So this will be 1, and this will be shifted to here, at n equals to 3, and then here it will come as n, so at n equals to 4, again this will be shifted at n equals to 4, and this will be n equals to 5, and this will be minus 1. Okay, so we know that DFT is periodic by, if is periodic by n. So here n is equals to 4. So that means this period. So I can draw the sequence also. So at n equals to 0, I don't know what is there. At n equals to 1, I don't know what is there. So the signal is 1. Sorry. So 2. This is, I'm drawing y of n. So this is at position 2, and this is with respect to n. So 2, then the component is C2, 3, 4, and at 5, it is minus 1. So we know that as because this is periodic with period of 4, so the thing that is here, that will be replicated after each of the 4 samples. So here we can say that the period at this particular location, it will start with 1, 0, -1, -2. So this will form another period. So if this is a period or with 4 periodicity, so the period that is present before this particular thing, that will consist the indexes of -2, -1, 0, and 1, and it will be replicated here also. So 1, then 0, then 0, and then at this particular location at -1. So now if I see this region, so now if I see this particular region, so I can see that y of 0 is 0, y of 1 is equals to -1, y of 2 is equals to 1, and y of 3 is equals to 0. So this is what the output looks like. So let us visit that what is the answers that is given. So our answer is 0, -1, 1. Representation in the time domain. Given any particular sequence, and the sequence, if the DFT is multiplied with any complex exponent, we'll get the circular shape by an amount of n. So here the amount was 2. Okay. So this is the last question for quiz 4. So which looks like x of z is equals to 1 minus 1. So this is z minus a square. So this is z minus a square. Okay. So I can write it as, let's take z squared out. So it will be 1 minus az inverse. So I can write it as z to the power -2 divided by 1 minus az inverse. Okay. So I can write this part as xz is equals to z to the power minus of, let us consider this is h of z, where h of z is equals to 1 divided by 1 minus az inverse. So if I get the inverse Z transform, it will be x z has inverse Z transform of x of n, and hc has inverse Z transform of h of n. So if I multiply a delay of z to the power -2, that means delaying with a unit of -2, therefore or let me be very precise. So I am multiplying z to the power -2. That means I am adding a delay of 2. So delay means x of delay means x of n minus n. So this is what delay means. So I am not delaying by -2. I am delaying by 2 unit. So it is h of n minus 2. So the question is that if I just find what is h of z, so it is, so there is a square that I have missed. So there is a square. So if I just find what is the value of h of n, then I will put every argument n minus 2 that is there in place of h of n. So I will get the output, that is x of n. So let us start finding what is the inverse Z transform of h of c. So for that, I can write h of c as 1 divided by az inverse multiplied with 1 minus az inverse. So let us consider this is x1z multiplied with, sorry, this will be x1z only, as because both of these representations are same. So this will be x1z. Fine. So if I take the inverse Z transform on both the side, it will be x1n convolution with exponent. So I just need to find the convolution of these of the inverse Z transform of these particular representations. Along with that, they have also written that mod Z is equals to mod. This is the ROC. So when let us consider this is the Z plane and this is the circle with uh, let us consider the uh, radius of this particular circle is A. So mod Z less than minus mod Z less than A is basically the converging nature of convergent nature of ROC. That means it is inwards. ROC inwards. So ROC inwards, it basically corresponds to left-sided sequence. So we need to remember that 1 minus AZ inverse has two different sequences, which basically represent the same Z transform output. This is basically the only distinction part. Just by seeing the ROC, we can just comment about the Z transform, inverse Z transform. So it is basically minus a to the power n. So u of minus n minus 1. So this is what the inverse Z transform looks like for this particular sequence, that is minus a to the power n u of minus n minus 1. Now I need to take convolution between these two particular sequences. So let me go to the next page. So h of n is equals to x1n convolution with x1n. So this will be minus a to the power n u minus n minus 1. Sorry. So this will be minus n minus 1 convolution with minus a to the power n u of minus n minus 1. Okay. So this minus will cancel each other and this will be plus. So let's solve the convolution part. So I can write it as a to the power k u of minus k minus 1. And then I can write it as a to the power n minus k u of minus n plus k minus 1. I'm just using the standard convolution formula. So the summation will run with a variable of k from minus infinite to infinite, and this is basically the convolution representation. So let's first start with this thing. So a to the power n, as because it is not dependent on the summation variable, so I can take this part out. So this will be a to the power n, and a to the power k minus k eventually lead to a to the power 0, that means 1. So this will reduce to u of minus k minus 1, u of minus n plus k minus 1. And k is running from minus infinite to infinite. This is what HM looks like. Now we need to find what is the resultant of these multiplication. So let's just consider the case of k equals to 0. So when k equals to 0, I have to see what is the thing happening inside this particular summation argument. So u of minus 1 followed by u of minus n minus 1. So u of minus 1 is basically 0 from the definition of unit step signal. So for n less than 0, we'll get no signal component over here. So the output will be u of minus 1 is equals to 0. And this is multiplied with this thing. So effectively the output is 0. Now let us consider k equals to 1. So if I consider k is equals to 1, so then it will be u of minus 1 minus 1 then u of minus n, and then 1 minus 1 is equals to 0. However, here also I can see u of minus 2 and then u of minus n. So again, this will be 0. So therefore, for k equals to 0 onwards, for the positive side, this argument inside this thing, it will be 0. So this argument vanishes. So we are bothered about the summation that is running from k equals to minus infinity to minus 1. And then uh, I can write it as e to the power minus k minus 1, then u of minus n plus k minus 1. So we have just solved the limit issue. What will be the final limits of this summation? Now, the summation is basically dependent on k. That is what we have seen by changing the limits of the summation. Additionally, the answer of this particular convolution also depends on the choice of n. That means for what value of n there will get the samples, on what value of n will get zeros. So we need to also take care about. So for that matter, let us consider with the case of n is equals to minus 2. So for n is equals to minus 2, I can write it as h of n. So you can consider this, I'm considering h of minus 2. I'm not writing h of minus 2 over here because I'm mostly bothered about what is happening inside this summation. So I will write it as a to the power n, and then k is equals to minus infinite to minus 1, u of minus k minus 1, u of, then it will be minus minus of minus 2, that will be 2, and that is minus 1, so it will be k plus 1. So at this particular condition, so here also I can reduce the sequence. For example, I will show you another case. For example, k is equals to, let's say, minus 1. So when k is equals to minus n, the thing that is inside this particular argument will be u of minus 1 that will be plus 1, then minus 1 u of minus n plus k minus 1. Therefore, I will get u of 0 multiplied with u of minus n plus k minus 1. So that is u of 0, we know that it is 1. So effectively, the output is u of minus k plus u of minus n plus k 1. So that means I can even simplify this particular equation as h of n is equals to a to the power n. Sum is running from minus infinite to minus 1, and then u of minus n plus k minus 1. Okay. So this is the reduced version, but still, as we have already told, that the final answer of this particular convolution operation will also dependent on the choice of n also, because we need to see that for which samples we get the output samples and for which position, for which indexes will get zero. So for that, we let us just find for the indexes. For index n equals to minus 2, I can write it as a to the power n. A is equals to minus infinity and minus 1, and then it will be u of k plus 1. Okay. So let me just go to the next page. So the summation is a to the power n, then k is equals to minus infinity to minus 1 u of k plus 1. So I can break the summation and I can start writing it as u of minus n plus 1. Then it will go, let's say, u of minus 3 plus 1, u of minus 2 plus 1, and u of minus 1 plus 1. So I can see this will lead to 0, this will lead to 0, this will lead to 0, and this will give you 1. So therefore, a to the power n multiplied with 1. Let's let n is equals to, that means for That means for n equals to -2, we are getting some samples. Let us consider n is equals to -1. So for that matter, what will be the case? So I can start writing a to the power minus n view of. So it was minus n plus k minus 1. So it would be minus n, so it would be plus 1, then plus k, then minus 1. And k is running from minus infinity to minus 1. So a power n summation u of k, and k is running from minus infinity to minus 1. So if we put the argument inside this u as minus values, so we know that u doesn't, unit step doesn't lie on the negative side of the index sample. So therefore the summation will go to 0, and therefore the output, final output will be 0. So in minus 2 onwards, we can get value. However, n greater than -2, so the output will be 0. So therefore, I can write the sequence as h of n. I will get some value over here. So 0 for, okay. So I will get 0 for n greater than, okay, so I will show you some more samples just before going to the final conclusion, so that there is no further doubts. So let's take another condition. N is equals to -3. So when we'll consider n is equals to -3, so for those conditions, we'll see that a to the power n, I guess someone has turned on their mic. So I can write it as k equals to minus infinity to -1, and then u of 3 plus k, and then there is, again, I can show you that k minus 1. So here a to the power n and u of, let's say, k plus 2. So that means here also you will get the values beyond you will get 0 beyond -3, and for k equals to -2 and k equals to -1, you will get the summation value. So therefore it will be e to the power n u of, the value exists will at this particular location, and all other places it will be 0. So u of -1 plus 2. So e to the power n, so it will be u of 0 and it will be u of 1. So, and both the places the output is 1 and 1, so 2 into a to the power n. So this is what the output looks like over here. So h of n, that is what I was commenting, that h of n, I can write it as a to the power n, then summation. So k is running from n plus 1 to, this is till -1. For example, here also you can understand over here. So I had taken n equals to -3, and for which values I am getting the final output at -1. That is the upper limit that I have taken over here, and the lower limit was uh, n plus 1. So that is, let us consider this n, I am taken capital N. So it is -3 plus 1. That is -2. So that means here also I am getting the value. So therefore the limits are justified. So n plus 1 to -n. And then the output is basically, you can see that the output of u of 0 is 1 and the output of u of 1 is also 1, as because unit step signal. So therefore this is 1. And the n value, it is basically -2. And over there, for example, n greater than we are actually dealing with the left sided signal. That is what we have seen in the initial part. So as because the ROC is basically mod z is less than mod a. So therefore I can write it as a to the power n and then summation 1 and k is running from n plus 1 to minus 1. And then I can write u minus n minus 2. So this minus n minus 2 will give me the right sided sequence part with a shift of 2. Okay. Now we had seen that x of n was h of n minus 2. So we just have got what is h of n. So we need to just put h of n minus 2 in all the argument spaces. So it will give me a to the power 8. So I can write it as a to the power n minus 2. And then it will give me 1 k equals to n plus 1, then minus 1, then u. I can write it as minus of n minus 2 plus 2. So it will give me a to the power n minus 2 and then summation k is equals to n plus 1 and minus 1 and then this is 1. So I have to solve this part also. So this is also remaining. So u of minus n. So we have to see what will be the output over here also. So we need to see the summation result. So to get the summation result over here, I can show it from this particular example. So here the output is 2 for when I consider n is equals to 3, the output is 2. So n equals to minus 3. Very sorry. So it is n equals to minus 3 and output is 2. So I can write it as the output would be the sum output. I can see over here that I can write n plus 1. It will give me minus 2 and then I can take minus sign over here. So it will give me the final output. So in this way, I can take the analogy and using that analogy itself, I can give you the final result. So this will be a to the power. So this output over here, let me show you like this. Yes, here I can state it a to the power n. And as because this is basically dependent on n, so let me write it as n now. So a to the power n and then it will be n plus 1 and there will be a minus sign over here. And then u of minus n minus 2. Find. Now we need to find the h of n minus 2. So I will freshly write it as a to the power n minus 2. And then I can write there is a minus sign over here. So the minus sign, this is, let us consider this minus sign over here. So this minus is going there. So n minus 2 plus 1 and then u minus n minus 2. So therefore it will be a to the power n minus 2 and then there will be n minus 1 u minus n minus 2. So this is what the final xn looks like. So this is quite a big problem. We started with the initial condition that is basically given over here. So xz was given. So we wrote that xz is equals to delay of hn. And then we tried to find the as 3 minus 3. Then output is equals to minus of n plus 1. So we eventually started solving this particular convolution operation, and we got to find that the convolution operation basically gives you definition of a signal. So from the definition, we got to know that for n greater than -2, every sample will be 0. So we will not consider those samples. And this is what the samples looks like. So I had written with a u of minus and -2. So this will give you left-sided sequence, or yes, this will give you a left-sided sequence with a shift of 2. And then this is the final representation. And as because we had multiplied z to the power -2 with h of z, so there will be a delay of 2 unit. And this is what the final xn looks like. Thus, by changing the arguments with n-2, which was there in case of h of n, all the arguments were replaced by n-2 over here, and this is the final answer. Let's see what is the answers that is provided by the NPTEL. So here, I don't think so I have place to get the answer. So this is what our answer looks like. So let's just compare. So minus of n plus 1, minus of n minus 1, so minus of n minus 1, a to the power n minus 2, and there is minus n only. As because here we can see that there is n minus 2, so n minus 2 plus 2. So this will cancel each other. So a to the power n minus 2, then n minus 1, and then of minus n. So this is basically matching with this particular option. So option C is the correct answer for this last question for this one. Okay. So let's move to the content of week 5. So in week 5, we have been introduced with some new representations, that is decimation, and it is linked with downsampling. Then we have also seen what is called upsampling, and we have seen, in contrary with that, we have seen what is called the interpolation operation. And then there is polyphase decomposition. And followed by that, we have seen that what is noble identities and all. But these three topics are very important as far as your exam is being concerned. So these three topics are very crucial. So I will just show you some glimpse of the content of this particular week. That is basically we have covered. So because it is beyond my scope that I can cover the whole thing. Even the time is also now it is 7:30. So I need to just show you the brush up things regarding week 5 content. So let's first start with the downsampler. So if we have a downsampling operation, so x of n, and let us consider it is giving you xd, downsample version of n. So we need to see what is the relation between xdn and x of n. So let's first talk about why this topic of multi-rate signal processing is relevant and which purpose we basically need it. For example, this multi-rate signal processing becomes quite relevant when we deal with the signal sampling rate change processes. For example, we have been given an audio signal. The audio signal is sampled at, let us consider 48 kilohertz. For example, let us consider an audio signal is sampled at 48 kilohertz, but the sampling, but the band limited, that is the high frequency. For example, if this is the signal and this is the signal frequency response. So the band limited frequency is, let us consider, line at 2000 hertz. So therefore, to sample this particular sequence as per Nyquist criteria, 4000 hertz is good enough. So if you go beyond 4000 hertz, then it is very high. But if we are sampling with 4000 hertz also, so this is good enough to work with the sampling rate of 4000 hertz or 4 kilohertz. So therefore, we need to downsample the signal from 48 kilohertz to 4 kilohertz. So therefore, the rates of the signals are changing, and this is why this topic is called multi-rate signal processing. That means whatever signal is coming into the system, this has different sampling rate. That is what is getting output at the that is what we are getting at the output. So the sampling rate of Xin and sampling rate of XD are different. So therefore, this becomes a quite relevant to study the multi-rate signal processing. So in this particular course in discrete time signal processing, we are basically concerned about downsampling or upsampling by integer factor. So it may so happen you are working with some representation where you need to downsample the signal at 4.4 kilohertz. So 4.4 kilohertz, or let's say you have to work with 4.1 kilohertz. So 4.1 kilohertz is not a integer multiple or integer division of this 48 kilohertz. So here comes the downsampling by an fraction part. So here we are not here the integer downsampling will not work. So you can always visit any other contents, so that basically downsamples the signal with a fraction value. So in this particular course, we'll be basically focusing on downsampling the signal by any integer amount. So with this, let's see what is the relationship between XD and XT. So we can see we are downsampling the signals. So that means we will drop the sample values at a regular interval. So, so this is 0, 1, 2, m, dot, 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 2m, and let's say this is 4m, like this. So what we'll do, so this is, let's say, x of n. I'm just bothered about I'm just showing you the positive side of the signal. Negative side, you can figure it out. Basically, the operations will be same. So what I'm doing, I will be sampling this particular signal with a sampling period of m. That means first I will consider in the output signal, if I draw it xt of n, so I will consider this sample. Then after m minus 1 sample, I will consider the second sample. That means this is x of 0, this is x of 1. But however, the index is now 1. So that means what was there in the original signal at mth location, that is basically shifted to first location of the new signal. Then I will consider this next sample at 2m. So at second index, I will get x of 2m likewise. That means what I am considering, x of n into n. So this is the decimation operation. In case of upsampling, this is the downsampling operation. In case of upsampling operation, if this is the input signal, and let's say it's E of n, or let's say it's U of n, or expander also you can call it. So x E of n will be related in what sense? So here I can show you that I am upsampling the signals. That means within two particular samples, I will inject some zeros. Initially, let us talk about injecting zeros only. There are several forms of upsampling or interpolation factors are there, by which you can take the average value interpolation and all those things. So let us first just work with the simple zero injection. So with a M upsampler, so in between this 0 and this x0 and x1, I will inject m minus 1 zeros. So I will inject m minus 1 zeros, and then I will get the next value. Then I will get x of 1. So this is xe of n. So that means it is represented as xn upon n. So we have taken the samples in a faster manner. However, the samples that we are taking, we are just injecting zeros only, and then we are getting the second value at mth location. So this is the main modification, the main outputs. So at what location we'll get the value? So this is m. So second value will get again m minus 1 zeros, m minus 1 zeros, and then at 2. So in some places I will get 0, in some places I will get x of n minus m. That means the value will exist at those particular locations. So what are these locations? So n is equals to 0 followed by plus m plus minus 2m plus minus 3m. So that means this n upon m should be integer. Doesn't matter whether it is on the positive side or negative side, it should be an integer. So therefore, I have written 0 plus m plus minus 2m plus minus 3m like this. So with this basic information, let us visit some questions which are related to week 5. So this will help you solving the quiz questions that is there in the current live course page. So this is the multi-rate system, and the multi-rate systems looks like this. So let me just draw the multi-rate system in the next page. So the question is that we are giving our input signal xn, and we need to and the output signal is yn obviously. So we just need to find what is the value at y index 0 after doing all these operations. So I will start drawing the. So first there is downsampling of 3, then there is and delay z to the power minus 1, that means delay by 1, then upsampling, then again there is a delay z to the power minus 1, and then add these signals, there is a adder. Here also there is a delay z to the power minus 1, then this will be downsampled z to the power minus 1, upsample, and here I will get yn, and here I'm getting the xn. So let's start solving this particular equation. So the output at each location I am annotating this them as A, B, C, D, E, F, G, H. So y of n is equals to d of n plus h of n. So we need to go along with dn and h of n. So let's start solving xn. I can write it as dot dot x of, let's say, minus 7, x of minus 6, x of minus 5, x of minus 4, x of minus 3, x of minus 2, x of minus 1, x of 0, x1, x2, x3, x4, x5, x6, x7, x8, x9. Okay, this much is fine for the supply. Okay, now what we are doing, we are downsampling the signal by 3 amount, or a downsampler with a factor of 3. So that would be more appropriate definition. So let's annotate the index, 0 index. So I will indicate the 0 index with this red arrow over here. So at this particular location, when I will downsample the signal, so I will get x0. So let's just write it from this side. So I will get x0 at same position. X0 sample will be at same position. Then from third point, I will get the next sample, x3, then x6, then x9, then dot dot. And similarly over here, I will get x of minus 3, then x of -6, then x of -9, and then dot dot. Then B is basically delay. So this is the zero location. So this location is very important as because we need to find the sample value at zeroth index of y. So this will be shifted. Now when this will be shifted, x0 will come over here. So this will come over here. So likewise x3, x6, x9 dot dot, and x -3 will now be at this particular location. So x of -6, x of -9, and dot dot. Fine. Then C is equals to upsample of this particular signal. So now at zeroth location, x of -3 is there. Fine. So when I will be upsampling the signal, upsampling means what? Upsampling means basically I'm injecting some samples. So if I inject some samples, I will get x of -3, and there will be m -1 zeros. So here I have shown that when I am upsampling by a factor of m, so there is m -1 zero injection. So here will the injection will be 0 0, then x0 0 0, then x3 0 0, x6. So this comma is looking like 1. So 0 0 x6 0 0 x9, and then dot dot. And similarly over here 0 0 x of -6, then 0 0 x of -9, and dot dot over here. So at C location, the zeroth position here also x3 will be there only. Now at D, so let's write what is D. So D, again there is a delay of 1 unit. So delay of 1 unit means this x -3 will shift now. So this will be x -3, and 0 will come over here at the first index or at the starting index. X of -3, then 0 0, x of 0, then 0 comma 0, x of 3, then 0 0, x of 6, and likewise. And here then 0 0, x of -6, 0 0, x of -9, and then okay. So now the center location has 0. Now we have to deal with, so D part is done. So the signals at this particular location we have evaluated. Now we have to go with this particular path. So if I move with this particular path, it is first it seems like there is a delay component with z of z to the power -1. That means delay by 1. So if I delay it by 1 at x -1 will come over here, then x0, x1, x2, x3, x4, x5, x6, dot dot. And similarly over here it will be x of -2, then x of -3, then x of -4, x of -5, x of -6, and likewise. The main thing is that the x0 has shifted by 1 unit. That means now the at starting index is x of -1. At starting index, the sample value is x of -1. Now let's move to F, that is your downsampling operation. So downsampling operation means I will get x of -1, then I will move to the third index. That is now this is 0 index, first index, second index, third index. So x of 2, then 1 2, then x of 5, likewise. And here also this is 0, 1 2 3, x of -4, then 1 2 3, it will be x of -7. So likewise this is F. Then I am doing a delay again. So here this was the center position. So now when I'm doing a delay, so the delayed signal is looking like x of -4, x of -1, x of 2, x of 5, dot dot, and similarly it is x of -7, and then dot dot. Now the zeroth index is x of -4. Okay. Now we have to consider what is h. So h is looking like there is a upsampling operation. So the upsampling operation will inject zeros, and the zero injection will be two sets of zero injection. So h will look like x of -4 will still remain in at the center location, and then two zeros x of -1, two zeros x of 2, dot dot, and then here will be x of 0 0, and then there will be x of -7, and then in the left hand side also dot dot. Okay, so we have found out what is D and what is H. Now our job is to find y of n, which is dn plus hn. So I can write y of 0 is equals to d of 0 plus h of 0. So at d of 0, so the at 0th location, the sample is 0, and here the sample is x of -4. So therefore, the output is x of -4. That means y0 is equals to x of -4. So this is the final output. Let us consider. Let us see the so y of 0 is equals to x of -4. So option C is the correct option. Okay. Now the second question is whether the downsampler operation, whether this is a linear or shift invariant or not. So let's just start solving this particular question. We have x of n over here, and this is because it is a downsampler. So the output, let us consider this y of n. So this will be n multiplied with m. So for linearity, we'll check with two different signals, and then we'll add the linear combination of the signals, and then we'll see whether the output is matching with the linear combination of the outputs when the inputs were applied separately or not. So y1 of n is equals to x1 of nm, and y2 of n is equals to x2 of n. Fine. Now C1 x1n plus C2 x2n, when we apply this linear combination input, so this y, let's say y hat, is equals to C1 x1nm plus C2 x2 nm. So therefore, this is C1 y1n plus C2 y2n. So that means this is obeying superposition theorem. Therefore, the system is linear system. So this is what the linear system looks like. So this is a linear system. So this non-linear part is gone. So this is also a non-linear part. So the operation option B and D are nullified. So we are left with the shift invariancy part. So shift invariancy check. So shift invariance means that when I delay the signal with an amount of n, and we get some output, and when we delay the output signal itself, if the operations are alike or yield the same output, so then we can say that the signal is shift invariant. So for that matter, let us write as, for example, xn is having x of -m, so -m plus 1, y equals x of 0, x of m. So okay. So x of 2m, like this. So when we what do you call, when we downsample the signal, we'll get something like this. So x of 0, x of m, x of 2m dot dot. Here also x of minus m, x of minus 2m, like this dot dot. Now what I'm doing, I'm delaying the signal by an amount of k, let's say. So I'm delaying the signal x of n minus k. So every sample is now shifted by an amount of k. That means what was there at x of 0 at the 0th location, the sample was x of 0. Now this sample is shifted by k an amount. So therefore, what was there in case of x of minus k, that will come to index 0. So for better representation, let us consider this is 0. This is minus k. And let's say this is 2, this is 1, and dot dot dot. Some samples are there. So this is x of 1. So I have to find x of n minus k. So that means the 0th sample will go to kth location. And the minus kth sample will go to 0th location. So that is what I am saying, that x of minus k, when I input this particular thing into the downsampler, in case of first sequence, we were getting the index 0. At index 0, we are getting x of 0. However, in this particular case, we'll get the index at index 0. The output will look like x of minus k, fine, then x of m minus k, then x of 2m minus k. Likewise, here I will get x of minus m minus k and on. So this is when input is delayed by k. Okay. Now let's someone is joining us. Now let uh, output itself yn is delayed by an amount of k. That means n now will be replaced by n minus k, and we know that yn is equals to x of n of m. So then when we replace this by x y of n minus k, we'll get nk minus mk. So that is what we are not getting over here. So this is when the, let's say this is y hat hat of n. So y hat hat of n is not equal to the output y tilde n when input is delayed. So therefore, the system is not time invariant, or I can say the system is time varying system, or let's say this time is basically shift. In many places, I basically loosely use these terms. So in case of digital signal processing, there is no concept of time. So anyway, this in the first class itself, I told that this could be rectified easily. So this is just shift invariant or shift value. So let's just see the options. So the system is linear. Okay, and the system is not shifting. So this option C. So option C is the correct answer for this particular question. Okay, so let's move to the last question. Let's move to the third question for week 5. So HN is a causal sequence, and the sequence looks like this. The sample at 0th location is 1, the sample at first location is 1. And g of n is equals to h of minus n. That means I can write it as this is just a time reversal operation. So minus 1, comma 1. And again, the 0th index is 1. That's because we are taking the time reversal operation. We are flipping the signal about the y-axis. So x-axis samples will be flipped around the y-axis. Then we are taking g of n minus 1. So g of n minus 1 is what? G of n minus 1 is delayed version of the sequence. So that means minus 1, comma 1. And this is at n minus 1, n equals to minus 1 location. Now this will be shifted to n equals to 0 location. So this is what g of n minus 1 looks like. So we need to find what is the output at this particular location. So here, let's say the output is A. Here, let's say the output is B, and here the output is C. So at A location, the output by A of n is xn convolved with g of n minus 1. So xn convolved with, so g of n minus 1, I can write it as minus of delta n plus delta of n minus 1. Is it not? So this is just the delta representation. If I show you the diagram, so this is the axis. At n equals to 1, I am getting plus 1. At n equals to 0, I am getting minus 1. N equals to 0. And this is with respect to n, and this is g of n minus 1. So I can write it as minus delta n and plus delta of n minus 1. So I can just put it over here, delta n plus delta of n minus 1. And then with the convolution operation, I know that it will be minus of xn and then x of n minus 1. So this is what we already have seen in week 1. What is the convolution operation? So x of n is convolved with delta n. I will get x of n. X of n convolved with delta n minus capital N will be x of n minus, sorry, this will be small n minus n. So this is what I'm getting at this particular location. Now I'm applying a downsampler. So at location A, I'm giving y a of n, and I need what is y b of n. So decimation operation. So y b of n is nothing but y a of 2n. So therefore, I can just interchangeably write it as x2n plus x of 2n minus 1. And in the next page, so let me just copy this part over here for the reference. So this is what the downsampling process looks like. So this is what the downsampling process looks like. Now we need to go for an upsampling. So we were giving yb of n, and I need y of n. Let us consider the output at this particular location is y of n. So I need what is y of n. So y of n is basically yb n by 2 and 0. So n by 2, sorry, n by 2 should be integer. That means n should be 0, plus minus 2, plus minus 4, plus minus 6, like this. That means this should be multiple of 2. And in the other locations, so I just write it as elsewhere. Other location I will get 0. So this is what upsampling process does. So I can write it as y of n is equals to minus x of n followed by x of, I can just replace the n with n minus n by 2. So this will be 2 into n by 2 minus 1 and 0 elsewhere. So minus of xn plus x of n minus 1. And elsewhere this is 0. So n by 2 is integer. This is the condition and this is elsewhere. Okay. So in this way, we can get the output at this particular location. So it is not just many people things that, okay, I am giving a signal y1 over here, and this decimation and this downsampling and upsampling process cancels each other and I will get the same signal. So that is not necessarily true. So you are always encouraged to work out some examples. You can take any sequence and then you can check whether in many places we'll see that, for example, upsample by 2 and downsample by 2, you will be able to figure it out when you will do the operation by your own by taking some particular signal and then you can just do the upsampling and downsampling process with the same factor with different factor and you can check that what is basically happening in those particular operations. However, I have taken another example which basically deals with the same thing. So let's just check what is the output for that particular question. So this is basically this very interesting question. So in this question, we can see that there is a Excel we are inputting in this particular system, which comprises of one upsampler of 5, downsampler of 3, downsampler of 5, and then upsampling of 3. So interchangeably, you can you may think that okay, I will get Xn only, but you may get Xn. But the thing is that in all the places, that means, for example, if this is your input, you may not get the exact Excel. You may get some values which are retained in Excel, some values 0. So you need to check out those particular things. And you need to consider those things very carefully. Otherwise, some people have seen that they consider that, okay, this is upsampling and downsampling operation. This will cancel each other. So anyway, I will get the same signal. So that is not. So that caution we need to take care. So let's first solve this particular question. So this is A, this is B, this is C, and this is D. So at Ya of n, I am doing an upsampling operation. That means I will be injecting some zeros. So injecting some zeros means x of n divided by 5 and 0. And now I have to be very careful about n by 5 should be integer. That means n should be plus minus, obviously I shouldn't write plus minus 0. So this will be 0 plus minus 5 plus minus 10. That means multiple of 5. And this is basically the other places elsewhere. Now when I'm doing xb of n, sorry, yb of n, so I'm doing a downsampling operation. So I can write it as x ya 3n. So that means x 3n by 5. And provided I have to take those samples only, which basically goes in the multiple of 5 locations. So again, I can say that 3n by 5 should be integer. So integer. So I can, again, it basically belongs to that particular argument. When n by 5 is integer, so obviously 3n by 5 will be integer. So this particular location only I have to take care of. So effectively 3n by 5 integer, that means n by 5 is integer. So we don't have to bother about this particular operation over here. That's because already we have taken care of this n by 5 integer part. So the next operation is yc of n. So yc of n is basically the operation as yb. So YCN is basically we are doing another downsampling operations. So if I do another downsampling operation, it will be YB n divided by 5. So it will be x of 3n. So now x of 3n already we have seen in this particular location, we are taking the samples from 5, 10. Already these are integer locations only. And if we multiply any integer value, I will get another integer. So here I don't have to bother about the x of 3n argument, whether this is integer or not. Anyway, we will be dealing with integer systems only. So in the next operation, y of d, or the final operation, y of d of n, or I can contrary say it as y of n. So over here, we can see that we are operating with a upsampler operation. So upsampling by 3. So let's just draw it as sampling by 3, and this is YD of n, and this was YC of. So upsampling operation means I will inject some values, inject some zeros again, and the amount of zeros is m minus 1. That means I will be injecting 2 zeros in between 2 samples. So in between 2 samples of YC of n. So uh, YD of n is equals to Yn is equals to YC n divided by 3. Okay. But the condition is that this n divided by 3 should be integer. Should be integer. That means n should be submultiple of 3. That means 3, 6, 9, etc. etc. Therefore, we need to consider this particular relation. That is, n by 3 should be integer. However, let me solve the uh, YD of n. So it is YC of n by 3. So what is YCn? So YCn is x of 3n. So this will be x of 3n divided by 3. So x of n. But the condition is that 0 elsewhere. Elsewhere. So the condition is that n by 3 is integer, and other places I will get 0. That means even if it looks like after doing, okay, we are doing the upsampling operation by 5, downsampling operation by 5, and then downsampling and upsampling, one may think that, okay, anyway, I will get x of n. So that may be true in some sense. You will retain some particular sample values of x of n. You will not get the exact representation. That is what I have shown in this particular example. You will retain those x of n which are there at these particular locations. That is, n is equals to 0, plus minus 3, plus minus 6, plus minus n, and all. So in these particular location, we get the same value that is there in case of x of n. However, in all other places, we'll get 0. So this is what you have to be very careful about. So just by seeing the upsampling and downsampling operation back to back, so let's just not think about we'll get the exact same signal. So we need to work out that what is the integer location and what are the locations that where I will get the samples. So let's check the final solution, that is x of n at n by 3 is integer. So x of n by 3 is integer. So other options are incorrect. So this is option A. So this is n by 3 should be an integer to get the final answer for this particular question. So let me just say. Okay, so with this, I have solved ample amount of question that basically comprises of solution of week 4. Additionally, I have also covered some of the questions that are related with the decimation, interpolation, upsampling operation, and the combination of upsampling and downsampling, with even with the combination of what you call the convolution operation also. So with this, we have covered several questions that will be helpful for you to solve the questions that are there in case of week 5. So if you have any queries, so you can please ask. You can unmute yourself and you can ask. So
Thank you.
yes, I guess you are saying something.
Nothing, sir. I'm saying thank you.
Okay. So with this, let us stop the meeting over here. And I will be conducting this live session on every Friday. So I hope you'll be joining in next Friday's session also. So let me just stop the recording over here. So